Okay, this video looks at Amphibole-only and Amphibole-Liquid functions within Thermobar. So as always, if you haven't already, you need to pip install Thermobar by uncommenting this. We're then going to load in various Python things, and we're going to import Thermobar as pt. So anytime we want to call a function from Thermobar, we'll do pt dot. Okay, so we're loading in data from a spreadsheet called Amphibole-Liquids. So we can have a quick look at that here. We can see the data is stored in sheet 1. And what we have is we have oxide data for the liquid phase, which is identified by _liquid. And then we have oxide data for the amphibole phase, which is identified by this _amp at the end of the oxides. And there's a sample name and a water content for water. Okay, so we're going to load in this file, so sheet 1. We're going to call the dictionary out, and then from this out we're going to extract all columns, call it my input. We're going to extract amphiboles, so using out open brackets amps, and call our amps, and then we're going to call our liquid data frame licks. And then we can see what these look like. So you can see here are the first 5 rows of your amphiboles. All of these columns are filled, which is looking good. Same for the liquid. The only empty columns are those that we didn't give it in the spreadsheet. So say you want to calculate amphibole-only pressures. As always, we can do help, pt dot, and then the name of the function. So we can run this. And this tells you that this is a function for amphibole-only barometry. It returns your pressure in kilobar. You need to give it amphibole compositions as a data frame. So if we remember, we loaded that in, and that's called amps now. You need to specify an equation for pressure. And these are all the different equations that are available. And for some of them, you're going to need to specify a temperature in Kelvin. And you can see I've just listed here which ones are temperature dependent. So it's only this P from Anderson 1995. Okay, so first up, let's use the new Rodolfi 2021 algorithm, which was released in Minerals. So what we're going to say is calculate amp-only pressure, specify the name of our amphibole compositions, here amps, and then we're choosing equation P is P Rodolfi 2021. And what you can see is that Rodolfi suggests using this input check. And if it's true, it's passed all of his input checks, and if it's false, it's failed them. And if it's failed them, here is at least one of the things it has failed on. So here, the recalculated total is less than 98.5. You've then also got the amphibole classification, which equation it has used, because what this algorithm does is it picks between that equation A, B, C, D, E from the 2012 paper. You've then got the water is calculated, and then all of the various amphibole things along here. Now, it might be that you don't want the ones where the input check is false to come out with a nan. We coded that in by default. But say you want to look at what the pressures look like for the ones that fail the input check. I mean, I wouldn't recommend you necessarily use these, but you might be interested in how well this filter is working, what pressures it's filtering out. So what we can do is we can add an extra argument into the function called Rodolfi filter false. What you can see now is that even for these ones that say false, it has returned a pressure. This one still yields a nan, which suggests that at some point in the calculation, it has thrown up a nan, either because it's dividing by a component that's 0 or any of these other sort of mathematical reasons. So this is a real nan. These nans were artificial that I added because it has failed this input check. Okay, say you want to use Ewan-Much's 2016 equation. Again, we can just run that, and it returns the pressure it's calculated, and then sort of the amphibole sites. Ewan uses a slightly different method for this. There's lots of different algorithms, so this is recreating his method here. You might want to calculate amphibole-only temperatures. So this is very similar. We're going to do pt, calculate amp-only temp. We need the amphibole compositions again, so that's the data frame we loaded in. You need to specify an equation for temperature, and in this case, we're specifying a pressure. It's 5 kilobars. And these are your temperatures. Now, in reality, you're probably not going to know your pressure. So what you might decide you want to do is say you want to use the pressure from Ewan's equation 2016, and use that to solve this. So the function calculate amp only pressure temperature allows you to iterate an equation for temperature and an equation for pressure. In reality, because the much equation isn't temperature sensitive, the function recognises this and basically only does one iteration. So it solves for P and then it solves for T using that. And you don't need to iterate anymore because that pressure isn't going to change as a function of temperature. So regardless, we can run that and you can see it outputs a data frame, pressure in one column, temperature in Kelvin in the other. Similarly, you might want to iterate equation T from Rodolfi 2012 and Rodolfi 2021 for pressure. This is what the supporting spreadsheet of the Rodolfi 2021 paper is doing. And you can see, as before, you have the first set returned. It sort of passed all these checks. You get a pressure and temperature, but all of these other ones fail. And again, if you wanted to look at which ones had failed or look at their pressures, you can type Rodolfi filter false and it will show you the ones that have failed the input check. Okay, Amphibole-Liquid temperature is very, very similar. If we look at the functions here, we can just do help quickly. And we can see now, as well as amphibole compositions, we need liquid compositions. And now we can also specify equilibrium tests. And if this is true, it will calculate KD FEMG, which Peterka suggests is an equilibrium test. So first, let's try it without. So calculate amp liquid temperature. You're going to specify your liquid compositions, your amphibole compositions, and an equation for temperature. You can see here we are, our temperatures come back in Kelvin. Now we're going to specify equilibrium tests is true. What it does is it shows you your temperature, your value of KD FEMG, and now it also adds a column saying whether it's within the range that Peterka 2016 suggests. So in this case, they all are, so you get a yes. So these equations are a little bit sensitive to meltwater content. Some of them have water terms, some of them just use hydrous fractions. So what you can see is in the input spreadsheet, we did have a water content. We were using 5 for all of these, 2 and 5 again. But you could overwrite it and set it at 1 and see what it looks like. So you can see it's changed only by about a degree here. Okay, similarly, we can just replace the word temp with pressure for Amphibole-Liquid barometry. And again, we can overwrite the water content from the spreadsheet if we so wish. So here are the pressures in kilobar. And as we did for Amphibole-only, we can iterate. So here we're iterating an equation for pressure with an equation for temperature. And actually it tells us here we've selected a P-independent and a T-independent function. So this is way of saying you're not actually iterating, you're just solving one and solving the other. But it's all together in this function so that if you do choose equations that iterate, you don't have to use a different function name. And here are your calculated pressures and temperatures. Again, we can overwrite the water content that we're using just by specifying H2O liquid equals 1. And you can see actually they're both pretty sensitive to water content. So our pressure has dropped by about 1.7, slightly more kilobars, and the temperature has changed by about 10 degrees. And as before, we can specify equilibrium test is true while we're iterating and while we're overwriting the water content. So there are also features for calculating melt composition using only amphiboles. So here the function is calculate amp only melt comps, and all you need to specify is your amphiboles. So what you see is you get a data frame back with headings corresponding to different equations for melt composition. So we have the Zhang equations here. We also have, for example, water in the melt calculated using Rodolfi, delta NNO calculated using Rodolfi. And you get this warning saying you must enter a value for temperature in Kelvin to get the results from equation 3 and 5 from Zhang and silica from Peterka. So we can do that. We can specify T is 1300 Kelvin. And you see now you get some extra columns because these calculations can be done. Now you might argue just using an amphibole you don't know your temperature. So what we can do is we can take advantage of the pressure and temperature equations we have for Amphibole-only. So here we're going to use the function calculate amp-only pressure temperature. We specify the amphibole compositions, an equation for pressure, an equation for temperature, and we say we don't want to use the filter of Rodolfi. We want a temperature for every amphibole. And then we use the melt function again, but now we specify that we want temperature from this data frame and where the temperature is temperature calculated. And you can see that. And now we might want to plot up the results. So here we make two subplots. On the first axis, we're going to plot the silica content from the Zhang equation 1 against that from Peterka. And then on the second plot, we're going to plot, say, silica from Zhang against titanium from Zhang. So what you can see is that these two equations are really, really similar up to about 70 weight % silica. And then Zhang starts to deviate up to these really high silica contents. And you can see generally the predicted relationship is that as you go to lower and lower silica contents, your titanium contents drop.